Dear learners, welcome to week 2, lecture 2. This lecture will cover that classification of cell surfaces and starting of that two-dimensional cell equations. Basically in week 2, lecture 1, we have covered that basic derivations of fundamental theorems of surfaces. Then I have derived that derivatives of tangent derivatives, basically the theorem of Radicals and Weingarten formulas. Then I have derived that Gauss theorem. In last lecture, the term 1 by R1 by R2 is known as Gaussian curvature. So, in the doubly curved surfaces, there will be two radiuses, one R1 and R2. If we take product of that is known as Gaussian curvature. Based on the Gaussian curvature, we can classify the cell surfaces. If R1 and R2 both are positive or both are negative, then we call it as a positive curvature and the cell will be defined as that positive curvature shell. Then the negative curvature, if any one of them either R1 or R2 is negative, then this product will be negative. Then we can say that in one direction it is negative, another direction positive curvature will provide a negative curvature to the surface. If R1 or R2, if any one is 0, then it will have a 0 curvature. Generally, the 0 curvature is on a like where only one direction curved surface cells like cylinder or a cone. When there is a curvature in one direction and other direction is straight, then this type of cell surfaces will have 0 curvature. And here you can see that center of curvature lies on the same side, so it is 0 curvature. When center of curvature is lie on the bottom side of a surface, then it will be a negative curvature. The second classification is based on the shape. So, basically three categories. One is surface of revolutions. There are number of cells which can be generated by revolving the plane curves around the axis. So, if we have this straight line and if we revolve around this axis, then a conical shell will be formed. If we have a line like this, then a frustum will be formed. If a straight line is revolved around the center, then a hollow cylinder will be formed. So, similarly a spheroidal and prolate spheroid will be formed. So, in the case of plane curve, this line sometimes it called generator line or a meridian line. So, in the case of cone and cylinder, the Gaussian curvature is 0. In case of ellipsoid, it is positive. In case of hyperboloid, it is negative. Next, some surfaces can be generated by translating a plane curve over the parallel to the plane containing the curve, that moving these lines over the surface we can generate the curve, for example like this. So, this type of surfaces can be generated just by translating the curved line over the curved surface line. So, this type of surfaces is known as translational surfaces. And then comes about the ruled surface. In the case of translations, this may be curved line parallel, but in case of ruled surfaces are obtained by translating a line along two curves, like when we have like this shape, then we call it hyperbolic or hyperboloid surfaces are known as ruled surfaces. Then we can classify based on developability. Generally, a surface is said to be developable if it has a zero Gaussian curvature. It means that that surface can be reduced to a planar surface without stretching or deforming the surface. If we are able to do that, like in engineering drawing courses, we used to teach that develop the surfaces. So, basically singly curved surfaces are generally developable surfaces. Like if you take a cylinder, if you open it up a cylinder, it reduces to a flat plate kind of thing. So, there is no distortion in that. So, that surface is known as developable surfaces, generally cones, prisms. So, all these are developable surfaces. A non-developable surface that requires stretching or cutting or deforming or collapse into a planar surfaces. Suppose if you want to make a 2D, then it will be a crack in that surface or maybe required stretching, that they will not smoothly joins. So, they maybe have some flower like pattern kind of thing. So, here it will be some gaps if you open it. So, these surfaces are non-developable surfaces. Non-developable surfaces have non-zero Gaussian curvatures. It may be positive, negative, but it may not be zero. Then examples are spherical drums represent a non-developable surfaces here. Already we have slightly discussed that cell can be further classified based on the geometry, like singly curved surfaces. Already I have discussed that singly curved surfaces have zero Gaussian curvatures, they have developability features, and they have one curvature. In doubly curved cell, we have curvature in both the directions, and like spherical cells or cell of revolutions like ellipsoid or paraboloids, they are known as doubly curved cells. There may be some self surfaces which may be combined, like if you want to take a patch, like in one direction it is a straight line, but other three directions it may have curved, like basically a roof of a building. So, in that case it will be a mixed kind of thing, that some part it is doubly curved and some part it is singly curved, or just forget about this. If we are talking about that a cylinder and above that there is a spherical dome. So, up to here it is a singly curved surface and a dome is basically doubly curved surface. So, in this way it will be a combined. So, if we want to study, we have to consider the things. So, in a table form we have classified based on surface, based on developability, based on existence of straight line and Gaussian curvature, positive, negative and 0. A surface which have positive Gaussian curvature is doubly curved and it is known as synclastic surfaces, also other name basically. And same way, if it has a curved negative Gaussian curvature, they will also have doubly curved surfaces, but these are known as anti-elastic. Then it is if Gaussian curvature is 0, then it is known as singly curved surfaces or flat surfaces. Flat surfaces also have zero curvature, like a plate. Flat surface is or like a circular plate, they have a Gaussian curvature 0. So, positive one is non-developable, negative one is also non-developable, but 0 Gaussian curvature has developable feature. And then existence of straight line, that already that transformability, that it cannot, they do not have any concept of straight line. When negative surface, they will have a two set of straight lines, like this, some we have straight lines will exist over there, and here is one set of straight lines exist. So, in this there will be straight line, but other direction will be curved one. These are the some examples that the surfaces looks like. How does they look? So, if for a normal surface we take a some section. For positive one look like this 0, and the negative one just turning up from that side. And for the case of developable, flat and non-developable, they will be already I have discussed that this figure may have some openings. So, they will not satisfy the compatibility equations, because if you try to develop this, the cracks will appear. So, these are non-developable surfaces. Then the surface of revolutions, basically through the gernator, and this is very most important figure you will find in most of the textbooks of shells, that how with the same concept of E1, E2 and X1, X2 and X3 we can generate different surfaces of shell. Like if we take a cylinder, then this red one becomes a cylinder and this surface reduces to a circular plate. If we connect this cylinder to the outer cylinder, then it will be a conical shell. If we convert with some, instead of a straight line, if we make from this cylinder to this some curved line, then it will be a doubly curved shell. And again over this line, if you take a straight line, then it will be a rectangular plate, and over this surface if you extend, this will be a cylinder with a generic profile. So, the profile may be elliptic or any kind of shape, oval. So, we can generate. So, through this figure it is shown that the most important part is that development of position vector and generation of the shell just by proper creating the gernators. Now, I just one or two examples. The very important part is that first we have to find out the position vector. So, in differential geometry, so it is slightly different, not like you go through that cylindrical coordinate system or spherical coordinate system when we convert to a cylindrical coordinate system or in rectangle coordinate system. Here basically let us say that is our system, that x1, x2 and x3, and you are having a cylindrical surface like let us say, and so in third direction is the longitudinal direction. So, if you want to have a surface over this, so basically if you want to take one patch and this patch will have if we want to like this also. So, basically in terms of this r, and if this makes an theta on this direction, and this is our, if we talk in terms of x3, x1 and x2, third direction is our longitudinal direction. Then basically x1 can be represented as r cos theta. So, basically there will be two parameters, one we call say that this line and another this line, there will be two parameters, one along theta, one along r. So, from there x and theta, or sometimes it is known as x. So, first we will have to take a patch x and theta, these are two curvilinear parameters, and from that we have to find out the position vectors. So, if this is the radius of a cylinder, then r cos theta into E1 hat minus r sin theta into E2 hat plus x E3, x is the length along the third directions E3. So, this is the position vector. So, most of the time that finding out the position vector is the most important or a critical one. So, for a given shell, first you have to find out a patch and decide the curvilinear parameters, and then accordingly find out this position vector. So, our aim is here not to find out the position vector, for our point of course that if suppose position vector is given to you, can you find out the first fundamental form basis E, F and G Lemma parameters and then L, M and N and then the Gaussian curvature. So, that just we want to do a small exercise. Let us say first derivative with respect to x, first parameter will give you E3, derivative with respect to theta will give you this thing, double derivative will be 0, double derivative with theta is this and mixed derivative is represented like this. So, what is E? E is the r comma x comma r comma x means r comma 1 dot r comma 1 it gives you 1, G gives you r square. Then normal vector n hat can be find it out using this technique. Then we have to find out n, m and n. So, L can be find it out using that our in actual it is n comma 1 dot r comma 1 if you remember. So, I told you that it can be reduced to r comma double derivative 1 and n hat. So, n hat we have created and then double derivative dot product to n and similarly mixed derivative and double derivative with theta. If you show that L, M and N will get and then radius of curvature along phi direction will be E by L, E L is 0 it gives you infinity and then r theta gives you G by n, G is r square, n is r, so it becomes 1 and then Lemma parameters will be A is equal to 1, A2 is equal to r. So, in this way we got and the Gaussian curvature becomes r1 into r2 basically 0, 1 over infinity is gives you 0. So, it is also clear that circular cylinder the Gaussian curvature is 0 and Lemma parameter is 1 and r and the radius in phi direction is basically we should write in x direction is infinity and theta direction is r. Same way for the case of conical cell the position vector is changes slightly instead of just x now it becomes x sin phi another vector phi is another angle. So, we can find out again the derivatives and mixed derivative and double derivative and obtain the E, F and G. Then L, M, N and from there we can find out the radius of curvature. So, Lemma parameters are almost same, but radius of curvature is slightly different here where in the case of circular cell it was just r, but now it rb plus x cos phi by sin phi. So, the purpose of to discuss these things here if position vector is given to you and you can find out the Lemma parameters and r phi and r theta. So, these are very much important for developing the shell theory that we must be aware what is r phi and r theta in terms of curvilinear coordinate system and what is the Lemma parameters. So, in the case of rectangular plate if you want to write position vector is let us say x e1 plus y e3 and then you can develop it for a rectangular plate. Similarly, one can develop for a circular plate and doubly curved surface cell. So, for even assessment point of view that position vector is given to you and then one can develop. So, basically that this differential geometry itself is a big subject of mathematics and there are lot of rules how to find out that position vector in differential geometry coordinate system or I would like to say that curvilinear coordinate system. So, it is slightly different. So, but our aim is not to explore that wholly the curvilinear coordinate system. Our aim is to just the basic theorems required for developing the cell theories. So, in that directions I am moving that first I have defined that curvilinear parameters and first fundamental form of surfaces, second fundamental form of surfaces and various theorems like Rodriguez theorem, Weingarten theorems, Gauss-Kodazzi equations. So, our aim is to just using those equations, but if somebody is interested to go beyond this, definitely they can go and they can read the books on differential geometry, differential calculus or curvilinear coordinate system. There are number of books, and for I think infinite kind of system of shells like elliptic, even just I would like to say that even for the case of a cylinder, let us say it is a pure circular and then elliptic, then oval. So, even this surface may be of any kind, though the other one is straight line. Same way in the cone also, in the sphere also. So, variety of surfaces are there. So, position vectors can be developed and corresponding, and these position vectors are easily available, that for a given, that even giving the curvilinear system means coordinates will be given alpha and theta, whatever they will. So, based on that you can develop. So, for developing shell theories, one need to have proper position vector system, means must be aware, they can take from the book or develop themselves, and then find out the R1 and R2, A1 and A2 for particular shell. These 4 parameters only be required. If we know these things, then definitely a 2-dimensional shell theory or a 3-dimensional shell theories can be developed properly. So, now in this direction, very first step, that development of a 2-dimensional model for a cell, let us take a shell element, and already in the very starting lecture I have said that middle surface will govern the shell. Basically, if we take plus half and bottom half and join together, then it will make a complete shell, and its middle surface basically governs all the property of the shell. So, we will try to develop our basic governing equations in the middle surface form. So, we have two curvilinear coordinate system, alpha and beta, and this is our red one is our middle surface, and R1 is the radius in this direction and R2 is the radius in this direction, and along the thickness or third direction which you called a normal, that is zeta, we call it zeta, and this we call it beta, and this is alpha, and the total thickness is h, and from the middle surface this may be minus h by 2 and to plus h by 2. This is doubly curved cell element. So, we have taken a small element, and first we will develop the basic equations like Lemma parameters or distortion parameters, and then we use it for developing the strain displacement relations. So, we have make a grid that a middle surface is taken and curvilinear parameters alpha and beta is taken like this, and then parametric lines are drawn parallel to beta and parallel to alpha. In my geometry, I am sorry that I could not draw in proper sense, but if you draw through basically through a program or through a scale, then definitely they will be aligning to beta and aligning to the alpha. So, basically this line is a line where alpha is moving, change alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 and so on, alpha 0. And these are the lines where beta is changing, let us say beta 0, beta 1, beta 2, beta 3, beta 4, beta 5. So, this lines is called alpha constant, and this line is called beta constant, that you say na, over this line beta 5. So, beta is constant here, alpha is changing, but over this line alpha is constant and beta is changing from beta 0 to beta 5. This is the rectangular coordinate system, that x1, x2 and x3, and position vectors are e1 hat, e2 hat and e3 hat. From there, that from this curvilinear coordinate system, let us say a point M whose position vector is r. After some time, or after applying the forces and subjected to the boundary condition, this material point moves to this point, which is this M dash, and now the position vector will be r plus dr. So, over this point, tangent to this will give you r comma 1, and tangent along this line will give you r comma 2, and normal to this surface will give you n hat, normal, surface normal, because this is our tangent plane, this is our surface normal. We are moving from point M to M dash, then a straight line will be a dr and a curved line will be ds. So, our aim is to find out the ds for this system. Now, we say that, let us say this is our reference plane. If you just going back, because we are talking about this kind of system. So, at the reference plane, that position vector is r, just slightly above, and let us say this is the along the thickness, that length is zeta. So, position vector will be capital R, and we are interested to develop in that sense. So, n hat, in that zeta moved, and this dotted line is basically our middle surface line. One view is shown here. So, this is R and this will be capital R. Now, we know that capital R can be represented that small r, which is a function of alpha and beta, and zeta times n hat. In that direction, the unit vector is n hat. Now, r is a function of alpha, beta and zeta. Zeta is the thickness coordinate, like we used to say na, some position vector r in rectangular coordinate system क्या बोलते हैं, x, y and z. So, small r is position vector of a corresponding point on the reference surface or the middle surface. Already I have discussed n hat is the unit normal vector from the reference surface to the point. Now, we want to find out capital dr. Before that, I would like to recall our basic theorems that we are going to use it here. The first two theorems, that theorem of Radicals, that n hat comma 1 is a1 by r1 into t hat 1, n hat comma 2 is a2 by r2 into t hat 2, and then these are the Weingarten formula, t hat 1 comma 1, t hat 2 comma 2, t hat 1 comma 2 and t hat 2 comma 2. So, r is written here. So, change in r, d capital R will be dr plus first function as it is, differentiation of this means change in that, plus n is as it is and change in this, because in curvilinear coordinate system each unit vector has their changes with respect to alpha, beta, they are not constant. So, change in unit vector will also take place. Now, ds square will be dr dot dr. So, our aim is as to that at some height from the reference surface, what will be the ds, because movement in 3-dimensional. So, dr is here, dot product of dr, you multiply dr dot dr and d xi, basically n dr d xi, then n zeta d and dr this, and then n dr d xi, then n square d xi square, then n zeta d and zeta, then zeta d and dr, then zeta and so on. So, we have got this equation 1. But in this equation 1, the small one, okay, we are aware that small dr dot dr we know, we can convert it to a Lemay equations first fundamental form. But what are this dr dot dxi or n dot dr or dr dn or n dot dr, then again n dot dn, then again dn dr, then again n dn and so on, dn dn. So, we have to explicitly write here alpha and beta are mutually orthogonal. So, it means that their r comma 1 dot r comma 2 is going to be 0. Same way n comma 1 dot n comma 2 is going to be 0. So, if it is orthogonal, mutually orthogonal curvilinear system, then their other derivatives means dot product of two tangent vector is going to be which are not same. For example, if you are talking about in rectangular coordinate system, I dot j is going to be 0. So, same way here. So, n dot dr d zeta. So, we are going to first. What is n? We can write just n, then dr is r comma alpha and d alpha plus r comma beta into d beta and d zeta. R comma alpha is T1, R comma beta is T2. I would like to say it here that obviously there will be n hat here and there will be t hat, because initially we are starting from there itself. So, but students have done just removing all these things, but they are same, there is no change. There is some arrowhead for a vector, these are all vectors. So, n is perpendicular to T1, so dot product is 0, then n is perpendicular to T2 also. So, this delta term will not give you anything. So, it is straightforward going to be 0 contribution. Then dr dot dr, r comma alpha d alpha, then r comma beta and r comma beta d beta. Already I have said that r comma alpha and r comma beta is going to be 0. So, it reduces to a in this form a1 square d alpha, a2 square d beta square, where a1 and a2 are known as Lamé parameters. So, I can just put it here. Then dn dot dr, if you remember that dn dot dr will be in second fundamental form, and then we can write properly. Here n comma alpha, so using the Rodriguez theorem, it can be represented that a1 by r1 into t1 and r comma beta is a1 into t1 hat, and similarly here n comma alpha and r comma beta we can write in terms of that form, because if you remember correctly that I have said T1 hat is r comma alpha in vector form upon me a1 and T hat 2 is r comma 2 upon me a2, like that. So, by T dot T1 is 1, again T2 is T2 1. So, a1 square by r1 d alpha 1 square, a2 by r2 d beta square, we got this contribution. Then n dot dn. So, again n dot dn. So, equation number 5, this will give you 0 because n comma alpha is perpendicular to n. Similarly, n comma beta is perpendicular to n. Then dn dot dn, n comma alpha and n comma beta, again this will give you a1 by r square, a2 by r square, and already that n comma alpha dot n comma beta basically mixed product is going to be 0. We have assumed that alpha and beta are orthogonal to each other. Then n dot dr, so already we have said that this is 0. So, now we can replace all the things from dr, from other contribution, 3 contributions, and n hat dot n hat, that gives you 1. So, from this is zeta contributions. Now, further mathematically simplify, if you see it is properly that like in our a plus b whole square can be written as a square plus b square plus 2ab, like that. These are also can be similar way, that twice of like this. So, same way these are mathematically simplified and can be written as a1 plus zeta by r ka whole square d alpha square plus a2 by zeta by r square ka whole square d beta square plus d zeta square. So, these two terms basically anybody can check it, thus if you open it, it becomes like this. So, ds will be ds1, ds2 and ds3. So, curved length along this and this, and we have a third curvature also. So, let us say zeta times. So, we can find out that moving from one position to another position, that ds will be ds1, ds2, ds3. One direction, two direction and three direction. If we want to find out that area of a reference plane, then it will be ds1 into ds2. So, from where we can get it, and the volume will be ds cross ds2 and ds3, and this can be obtained like this. But here point to be noted that if you want to correlate with the previous system, that where we have obtained in the case of the first fundamental form, it was a1 square into d alpha 1 square plus a2 in the 2D case basically. So, basically we have going to replace this a1 with the small, so that there will be no confusion in future. Otherwise, we will call this a1 whole product and this is also a1, then they will be a confusing one. So, already I have told you that in the present case a1 is this one. There I find that in some of the books this a1 is complete this a1 and it is also again a1. So, that creates a problem. So, instead of a capital A1, we are going to replace it small a1, where this is the reference plane. From now onward, if I call capital A1, that means A1 1 plus zeta by R1. Capital A2 means A2 plus zeta by R2. Capital A3 means 1. So, the elemental area of a middle surface where zeta is 0. So, you can put zeta is 0 and we can find out small a1, a2, d alpha and d beta. After that, once we know a1, a2 and a3, already we have expressed that the volume ds1, ds2, d3, a1, a2. So, here I will replace a1 small a2 1 plus zeta by r1 into 1 plus zeta by r2. Here again a small a1 small a2 1 plus zeta by r1 and 1 plus zeta by r2. So, with this I end this lecture 2. In the lecture 3 of week 2, we will start that strain displacement relations in curvilinear coordinate system, and using our this a1 and a2, we will simplify the strain displacement relations and will use for developing the shell theories. Thank you very much.